Okay, so welcome everyone. Welcome back to MOPA for the fall 2023 semester. This is our first talk for the semester, and we're very happy to have Elliot Glazer from Harvard here to speak on coin flipping on models of arithmetic to define the standard cut. As you can see, I'm a little bit rusty, so apologies. Go ahead, Elliot.
Okay. Hi, everyone. Uh, I have never been to this seminar before, and I'm not sure to what extent what I'm going to show you how it fits into the standard paradigm of model theory because I'm not a model theorist. I do a lot of set theory, but I thought this was a fun talk, so that's happens to be about models of Peano arithmetic, so I thought it'd be fun to give it to the Models of Peano arithmetic seminar. And let's see how it goes. So this talk is about formalizing a intentionally vague claim. So here is the claim that I'm going to make and defend for you guys today. That the standard cut of a model of Peano arithmetic, or even Robinson arithmetic, is uniformly definable with respect to a randomly chosen predicate. Well, okay, what do I mean when I say randomly chosen? The idea that I want you to be imagining is you're handed a model of arithmetic. You don't have direct access to the background universe of sets, and you cannot directly quantify over subsets of this model. You can't directly talk about whether or not it's even the standard model. But I will hand you a coin, and you can use this coin to do a legitimate coin flip on every element of this model of arithmetic, and in doing so, assign it a randomly defined predicate, where the predicate is the set of heads. And I want to claim that there's a uniform way to isolate the standard cut from this predicate. The more philosophical thesis that I'm trying to justify with this is that we can reduce the concept of Platonism regarding arithmetic, belief that there's a true model of PA, a minimal one out there, the standard one, to this idea of Platonism regarding randomness. So while we will be speaking necessarily to formalize some of these arguments about a background universe of sets, I'd like to keep in mind a more open perspective to an idea that I can't really explore here, but the idea of as directly as possible, just considering what it means to coin flip on a set. So what's the simplest way we might formalize this claim? Well, if the model was countable, we can formalize and verify it with Lebesgue measure. Lebesgue measure also happens to be equal to the completion of the product measure of countably many equal weight coin flips. And this is actually well defined for arbitrary x, even uncountable x, that we can talk about the product measure on x many instances of coin flipping. Unfortunately, the product measure here is very coarse. For example, if you take x equals r, it's not even the assertion. So if I take x equals r and I were to coin flip on r via the product measure on r many coin flips, the event there are uncountably many heads is actually non-measurable because the product measure really only allows us to assign probabilities to things that ultimately reduce down to some countable subset of the coin flips. So it doesn't really tell you a whole lot of interesting things, and it probably won't be much of a surprise to you guys that we cannot formalize my original claim with this product measure. We're going to have to come up with some alternative notions of negligibility to make sense of this. And this is important to me. I don't want to only consider the case that the model is countable, because to even talk about whether a model of arithmetic is countable, you already need to have a background true omega, which kind of begs the question regarding justifying Platonism of arithmetic. So I'm going to need some argument that works for general M. But for now, we'll focus on the countable case. Let's introduce a notation. So, of course, we will identify its standard cut with omega. And the relevant language we're going to have in these models is plus and times, the original structure that made it a model of arithmetic, plus this new unary predicate P that represents the heads of these coin flips. And we're going to denote the set of predicates for which phi fails to define the standard cut. So I just introduced this compact notation SM phi. These are the predicates which will incorrectly determine the standard cut by this formula. And then by taking the union along all properties, we identify we can build a set of all the predicates which by some means define the standard cut. I don't mention this in the slides, but an exercise, even if we allow so if we expand SM to allow our predicates to define the standard cut even with respect to a parameter in or a finite number of parameters in the model, that doesn't actually change the definition of SM. It doesn't matter whether or not we are allowing parameters here. All right, so let's start off with this original claim. So I have a countable model of arithmetic. And just to be unnecessarily optimal, I'm only going to assume it's a model of Robinson arithmetic. After this theorem here, I'm going to only be talking about PA models, but there are Robinson generalizations for everything I'm saying today. But here I'll be pedantic and only assume Robinson arithmetic in our model. And here is the formula that we're going to use. It's going to be called phi 0. We say that, so after we coin flip and put this random predicate in our model, we are going to define the set of objects in this model such that, looking at the restriction of this predicate to below a particular point, is that restricted predicate girdle coded by one of the objects in this model. And I'm going to claim that almost certainly this will correctly identify the standard cut of the model. Okay, so first off, there's something that's going to be absolutely true. There's no probabilistic assertion here. No matter what the predicate we choose is, this formula will be satisfied by every standard natural number. Because for every standard natural number, doesn't matter what predicate we put below it, that's going to be a standard finite set. There's going to be a higher up standard number that codes it. So we have gotten at least the standard numbers. Okay, so why is it only going to be the standard numbers? Well, there's only countably many ways in which this can fail. That is, consider each possible instance of one of the non-standard numbers, x, and some c, which we're going to try to encode this non-standard. There's infinitely many things below it. For this to correctly identify the predicate below x, that requires infinitely many coin flips to have been called correctly. So for any particular c and x, this is a closed measure zero set of predicates. And considering all countably many ordered pairs, take the union of those, we see that this failure set, SM phi 0, is a null G delta set. So we're done. This formula works for countable models. But we can also see how this kind of argument isn't obviously going to generalize well once we start taking uncountable models, because then we're taking an uncountable union of things, and the argument breaks down. We're going to have to approach this from a different angle. And not only are we going to approach it from a different angle, but we're even going to have to we're going to have to use a different definition here of what we mean by absolutely negligible. So here's the major obstruction. And that is what happens when we take our model to be a countably saturated model. So take any M, a countably saturated model of Peano arithmetic. Then no matter what formula you try to use, the set of predicates which fail to define the standard cut under this formula is outer measure 1, where outer measure 1 is with respect to the product measure on m many copies of the Fair-Bernoulli. So how do we show this? So to show this, it suffices to show that there is no non-trivial countable support cover of this set. And when I say a countable support, a family of subsets of 2 to the m is countable support if you can determine whether it's in the set by looking at only countably many points in M. So let's describe such a set. So we're going to fix a countable subset of M and some function from this set to 0 to 1. So a partially described function from the universe to 0 to 1. Well, by countable saturation, there is some C in the model, which is strictly an upper bound for A, and which codes a predicate that, restricted to these countably many points, successfully predicts whether or not F sends it to 0 or to 1. Clearly, this predicate is definable with parameters. So if you look at the structure, m plus times with this predicate, it's a conservative extension. So just like the original model, this fails to define the standard cut. Notice that we never even used anything particular about our formula phi. So actually, this is even more severe, that SM, the union of all possible that the union of all possible no matter for this, I'm just switching the quantifiers around. For this one arbitrarily chosen predicate, it is not true that any of the formulas that we could use will define the standard cut. Therefore, the only countable support cover of SM, the general set of all failure predicates, is only covered by 2 to the m, so its outer measure is 1.
Can I ask a question on that slide?
Sure.
Does the same proof work for omega 1-like models? Because it looks like all you need is that any countable set has some upper bound. That's only usage of countable saturation that I'm saying.
Not just the upper bound part, but the fact that this object successfully codes, Gödel codes the predicate restricted to that countable set.
Mm-hmm.
I don't think omega 1 length. I don't see how just from omega length you can justify such an object exists.
Yeah. Okay.
Okay, so try 1 failed. The product measure was too coarse. Well, here's another way to think about randomness that also isn't restricted to the countable world. How about we just do this coin flipping in a forcing extension of our universe? And let's try this in 2 different ways. One thing we can consider is take our model, collapse it to be countable. Now we're in a larger universe of sets. And in this universe, now the model is countable, our original formula phi 0 will correctly define the standard cut on a Lebesgue measure 1 set of predicates. That is technically a mathematically correct formalization of the original claim. Here's another such argument. Instead of taking the collapsing extension, take the random extension. So force with the product measure on 2 to the m and get the random extension by a random predicate on M. And then with a little bit of work, that we can show that the generic filter will necessarily be a predicate on M for which phi 0 defines the standard cut. So these are mathematically correct, but I don't think that either of these are a philosophically satisfactory justification of my original claim. Because both the cases, we pretty severely extended the universe. In fact, we added new reals to it. So if we're going to really literally follow this logic here, what I've really shown, quote unquote shown, is that if you coin flip on M and generate a random predicate, it defines the standard cut. And furthermore, this predicate's intersection, the standard cut, is a real that doesn't yet exist. This is my frustration with attempting to formalize concepts of randomness via forcing. It's essentially taking for granted the perspective that we're all currently already in a countable world, that we don't currently have a completed notion of the continuum or power sets of anything. And I disagree with this view. I disagree that this is the right way to think about randomness. I think that if I'm talking about choosing a random element of the real line, I'm looking at this set, R, and I'm picking a point in it. I'm not picking a point in some hypothetical extension of the universe that recognizes that, no, we were wrong about the universe in the first place. So I think there's a lot of philosophical baggage to trying to formalize randomness arguments via forcing, and will not actually be willing to consider extensions of our background V. So V is fixed. And if I'm coin flipping on an uncountable model of arithmetic, it's going to stay uncountable because we can't collapse it. So how else can we make sense of the idea that this set of exceptional predicates is negligible? It's not necessarily going to be measure 0 in the sense of the product measure, but there are other ideals that it could be in, ideals that could also have some intuitive claim to only containing within its negligible sets. That is the approach that I'm going to be taking for the rest of this talk. So first off, so take an arbitrary set X. X need not be a model of arithmetic, just any set X. You can always consider 2 to the x as being a group by appending to it the addition operator, where plus is mod 2 addition. So we're going to define a subset of this group to be I small, I being some arbitrary index set. If there is some injection of this index set into 2 to the x, or group, such that the translations of S by the outputs of this injection are pairwise disjoint. So, for example, I could be omega. So to say that something is omega small, or I'll probably say aleph not small, since it's really just cardinality that matters here. To say that S is aleph not small simply means that there's a countably infinite sequence of disjoint translations of this set. And in the case of X is countable, we can also talk about some more general notions of smallness. One of my personal favorites being perfect smallness. We're going to say a subset of 2 to our countable X to be perfectly small if there is a perfect set of disjoint translations of it. And I'm going to claim that for infinite index sets, I smallness, and especially perfect smallness, have a pretty strong intuitive claim to formalizing as being a formalization of a set being probabilistically negligible. Because if I were to choose one of these subsets at random, here we have infinitely many equally likely outputs by translation invariance. We have infinitely many equally likely outputs that are mutually exclusive, equally likely to our original set. And I think the case is even clearer in the case of countable X and perfect smallness, where within this perfect set will necessarily be some copy of the counter set. And using the counter set, essentially we can identify each of these perfectly many translations of x with possible outputs of a countably infinite sequence of coin flips. So roughly speaking, if a set is perfectly small, then the probability that a randomly chosen x is in it is at least as unlikely as pulling out a countable sequence of coin flips all being heads. So that's my rough argument. We're going to see that mathematically, though, these things are a bit messier than the usual probabilistic notions of negligibility that you might be more familiar with. But first off, we'll also introduce one other type of smallness. This is going to be called absolute negligibility. So take a class of finally additive probability measures on 2 to the x. And we're going to say that a subset of it is absolutely negligible with respect to C if every measure in this class can be extended to one that assigns this set 0. In other words, it's formalizing the idea that, all right, I got this measure. It doesn't measure S yet, but inevitably, once we figure out how to evaluate enough of the probabilities regarding coin flipping on X, it is inevitable reality that eventually you're going to assign 0 to this particular event. And we're going to focus on 2 cases. One being the class of translation invariant finally additive measures, and the more restrictive class we're going to consider is sigma additive translation invariant measures. Of course, sigma additive here just means it's actually a measure. Always a bit frustrating that I have to throw in the phrase finally additive every time I want to have less assumptions about the measure, but that's just how the terminology evolved in this field. All right. By the way, I mentioned before that I'm a set theorist. More specifically, I'm a choiceless set theorist. Which again makes it kind of funny that I'm speaking to a Models of PA seminar, because in my experience, model theorists are the logicians who are most attached to the axiom of choice. It feels like so much of the technology in this field utterly requires choice to get anywhere. You know, you use it like five feet into model theory 101 in the proofs of completeness theorem and maximum generality for arbitrary languages and the Lowenheim-Scullin theorems. Well, you don't got that here because I'm throwing out choice. And the reason I'm going to throw out choice is because choice has a lot of paradoxical consequences regarding randomness. For example, the Banach-Tarski paradox implies that there is no finally additive isometry invariant probability measure on the unity cube. And we're going to, in a few minutes, I'll actually give some examples of some counterintuitive consequences of choice regarding the notions I just introduced. I'm not saying that these theorems that I'm talking about today are of no interest to someone who's, fully committed to choice, but I just think it's good practice not to include the axiom of choice in our base theory when we're trying to get into a fundamental understanding regarding the nature of randomness. So we don't have access to most of model theory, but some things do actually work out kind of nicely in ZF. So when you're thinking about what an arbitrary model of arithmetic looks like in this strange choiceless background theory of sets, here's our characterization. A set X can be given a Peano arithmetic structure if and only if this set is infinite, orderable, and is its own square. Just to sketch out why this is true, one direction is, okay, so I've got a model of PA. Clearly, there is an order. Clearly, it's infinite. Those are all first order. And internally use the Gödel pairing to get a bijection from XX squared. The other direction is by Mostowski models construction, where if you have a linear order that is of equal cardinality to its own square, then you can check that when you do an EM model construction with that order as being our set of indiscernibles, it never increases the cardinality of X. So that's why we have this characterization available to us. So I just want you to have that in mind, even though we have thrown out choice, and choice is often used to prevent a lot of really pathological behaviors of infinity. You don't have to worry about that. All the infinities relevant to this are actually still are explicitly shown to be nice infinities. There's not going to be any amorphous sets involved in the theory of models of PA.
So how much of PA did you actually use there? I mean, not all that much, right? You want the pairing function. Nice for that direction. How about the other direction?
Oh no, this is very general. Yeah.
Yeah, I mean, this
So
could be Robinson arithmetic or something, or
the general fact is that for any countable theory that has some infinite model, then it has models of all infinite orderable item power cardinalities. And even more generally, if I have an uncountable, well-ordered cardinal kappa, and I have a theory with kappa many symbols with some infinite model, then it has a model of any particular cardinality that is orderable, satisfies x equals x squared, and such that kappa injects into that set.
so it's sort of like a Lowenheim-Skolem statement, except with all of these terms and conditions attached to it about the cardinality, right?
Yeah, this is about the best you can hope for as a
Yeah.
ZF analog of the Lowenheim-Skolem theorem.
Thanks.
Yeah, so you can do all so model theory doesn't just collapse the moment you take out the axiom of choice. But that's a whole nother topic for a different day. This is the relevant part for models of PA. And a little bit about negligibility notions and their closure properties. So a reminder that we are now working in ZF world, and I will be very explicit anytime I have to use countable choice to justify a claim. So purely in ZF, the all if not smallest subsets of 2 to the x generate a non-trivial ideal on 2 to the x. And the set of Cn absolutely negligible sets are just already an ideal. You don't have to generate anything. Reminder that C sub inv is the class of translation invariant finely additive measures. So again, these are the sets for which any such measure extends to another one that signs the set 0. And with countable choice, we further have that the C sigma inv absolutely negligible sets are an ideal. It's more or less impossible to say much of anything about C sigma inv, about sigma additive measures, if we aren't even willing to assume countable choice. It's not even true that the singletons of the real line, or that it's not even a ZF theorem that there exists a set such that the singletons of that set generate a non-trivial sigma ideal. So we're going to want at least some choice every time we talk about that thing. Anyway, once we have countable choice, something that doesn't get resolved is whether or not these ideals generate any sigma ideals. Oh, that's a typo. Any of these 3 ideals. So even in the case of x being the natural numbers, it is ZF plus CC does not decide whether any of these ideals can be generate sigma ideals. So in the solving model, it's not hard to check that these are all sub-ideals of the null ideal. If you have a positive Lebesgue measure set within a probability space, there is a clear fine upper bound to how many disjoint translations it has. And clearly you can't extend the Lebesgue measure to one that assigns this already measured positive measure set to a measure 0. And because they're sub-ideals of the null ideal, clearly they generate some sigma ideal. But under full choice, this is going back to how axiom of choice provides regularity up to a point. Countable choice DC, they give you regularity. But then we get pathological consequences again. because now we have that the continuum is a countable union of sets, which are all of these. The continuum is a countable union of perfectly small sets, which are also absolutely negligible in both sentences I gave. And choice also proves that there is a maximal perfectly small set, sort of by these sorts of arguments or by a generalization of the well-known transfinite recursion construction of a Bernstein set under the axiom of choice. Well, with this context given, I can now finally state how I'm going to formalize the vague claim I made at the beginning of this talk. For all models of Peano arithmetic, and we are again going to be using our formula phi0 defined at the beginning. And I'll actually, I might as well just show that again. Phi0 is this formula here, that there exists a C which Gödel codes the predicate up to this particular point. So using that formula again, our definability of the standard cut theorem is that for an arbitrary model, this formula defines the standard cut almost certainly. Almost certainly.
Sorry, could you put that formula just one more time?
Oh, sure.
Yeah, that's another key, and to start. Let's see. Uh,
Yeah, this is I'm not always a huge fan of giving online talks.
okay,
I sure
so
like to have certain key slides always available to the audience, but
all right, so
here
X down is the subset of it's all elements of your model that are less than or maybe less than or equal to X, right?
Yes.
In that model, right? And then that's some initial segment, right? And then you have some predicate, it's denoted by P in your formal language, and in practice it's your thing that you made by coin flipping. And you can look at that and just restrict attention to all of to the downward set of X. And what? Oh, and you want to code that within the model itself via a Gödel encoding, right? And that's what this phi says, right? Is that you can do it for that particular X as opposed to some other X. Okay. Okay, thanks.
That's it. Where am I? Right. So we're gonna always be using this formula as our way of defining the standard cut from henceforth. And when I say that it will almost always define the standard cut, here we mean all except a continuum small set of counterexamples or a C in absolutely negligible set of counterexamples. Then under the appropriate assumptions, we can also get the other versions, that if M is countable, we can further say that the set of counterexamples is perfectly small. Or if we assume countable choice, we have that C sigma n absolutely negligible. So under all these reasonable notions of negligibility, we have that almost always you get the right cut. To begin the argument, we're going to start paying a little closer attention to what the set of counterexamples looks like. So we're defining S to be the set of all predicates on our model with the property that it is not true that under phi0 it defines a standard cut. And we've already mentioned that that phi0 will always be satisfied by any standard number. So to say that a predicate is an S, that means there's got to be at least one non-standard natural number that its entire predicate up to that point is encoded by some object in universe. So what we're going to actually show is that the set of counterexamples is a subgroup. So to show this, well, first off, because all elements in this group are order M-2, and clearly the empty set is in S. So all we have to verify is addition is closing addition. So take two such predicates. take witnessing x1, x2, c1, c2, x1, x2 being non-standard numbers for which there are these Gödel codes explaining the predicates up to that point, and take x1 below x2 without loss of generality. Then you can easily define from these two codes, C1 and C2, another code for the addition of these predicates up to the smaller one, x1. So it's additively closed. Great, it's a subgroup. And it's a proper subgroup. There are many things that this subgroup misses. For example, every subset of the model, which is just an infinite subset of which is an infinite subset of the standard cut, then we immediately see that S intersect this must be empty. Because let's say we did. Let's say I have an infinite subset of natural numbers, and I have some non-standard number. Well, if there was a code for this predicate up to this non-standard number, that just amounts to defining a cofinal set of natural numbers, which is clearly impossible. And finally, the final observation is going to be that we take any perfect chain in 2 to the omega minus the empty one, so these are all infinite. Then by identifying points in this with their cosets in G mod out by this subgroup, we see that this index set is actually F2 linearly independent. Where by F2 linear independence, you could think of this subgroup as being an F2 vector space in the immediate sense. So what does this get us? Well, it immediately verifies the smallness requirement of the theorem, that this set of counterexamples is 2 to the Aleph naught small, because I has cardinality 2 to the Aleph naught, and the translations of S by these are disjoint. And if M is countable, then in fact S is perfectly small because I is just a bona fide perfect subset of this space, which is homeomorphic to the counter space. So the more interesting part is justifying the absolute negligibility claims. To do this, we need to consider the ideal J on 2 to the M defined by every subset of, which contains every subset of 2 to the M, which can be covered by countably many translations of S. Just give a moment to keep track of this definition. The key thing about this ideal is everything in it is continuum small. To prove this, take some set of 2 to the M, consider a sequence of points witnessing that it is within J. And now take those points and look at the subgroup that they generate over the quotient group by S. Well, it's countably generated. It is certainly a countable subgroup of it. So we still have continuum many points in this index set that are not removed. And I with H removed is a continuum sized witness that A, in fact, this larger H are continuum small. I'll give you a second to see why that is. with this lemma in our hand, we can finish the proof. So let's start off with the finally additive case. I've got some finally additive measure, any finally additive translation variant measure on 2 to the m. And the first thing to notice is that if I have a set and it is both continuum small and measured by this measure, it must be assigned measure 0. Knowing this, we can now define our extension of the finally additive measure. The extension is, it's basically what you think. It's the minimal measure generated by the original plus assigning everything in J to 0. More precisely, for any B, we could declare to have measure A if, I just realized that choosing to use lower and uppercase letters was not an ideal choice for orally presenting these arguments. We say that capital B has measured lowercase a if some capital A has measured lowercase a, and for which A and B differ from each other by a set that is in J. And the only thing that needs to be done here is verify that this is a well-defined measure. It's well-defined because if you take any two separate values, two separate A's, which witness that B has some particular value, they must be measure 0 apart from each other. Measure 0 apart in the sense of the original mu. Finally, now let's assume countable choice. And now we're going to assume that our starting mu is sigma additive. Then J, the same J that we've been using from here, is in fact a sigma ideal. This is actually why I define J in terms of countable unions rather than finite unions. Of course, a countable union of countable sets is not ZF provably countable, so we did have to use a countable choice here to verify that this thing is in fact a sigma ideal. But it is. So the measure generated by our starting measure, Nj, is a sigma additive measure, extending mu, and having all the other required properties. In particular, these measures will assign our set of exceptional predicates a measure of 0, as desired. Finally, I'm going to give one last remark about forcing. So let's go back to some model of set theory, which will not be an omega model. Then the funny conclusion we have here is that for almost all predicates, for almost all P subsets of omega as computed in this non-omega model, M appended P is not a random real extension of M, where almost all was in any of the 3 senses I gave for the main theorem. This is true for a trivial reason, that P would define the standard cut of M, while a random extension does not. So there's clearly a lot of a huge distinction between this sort of approach to generalized randomness by forcing over models versus working within a fixed model and studying these generalized negligibility ideals that can be computed within V. And that's it for my talk today. I've listed here the sources of this negligibility terminology. Zach Krasuski has studied perfectly small sets, though his terminology doesn't line up one-to-one exactly with the way I'm using it. I'm technically using what I'm calling smallness is what he calls tube smallness. And Karyashvili has written a lot about these notions of absolutely negligible sets under various measure theoretic contexts. Thank you.
Okay, let's thank our speaker, using either to unmute or use the emojis, whatever you prefer. But thank you so much. That was very, very nice. And I'll open up for questions. I'll keep an eye out on the chat, and if anyone has raised hands or anything like that. So yeah, feel free to or feel free to unmute.
By the way, I'll take the time to show off my shirt. I don't know how visible it was, but it's a cute little set theory shirt that I got from Vsauce. And see if you can see what the background back says.
No.
Make it alphanol. Okay, I can do
Yeah.
that. Yeah, and part of it is cut off by your chair, but it's okay. Got the gist of it. All right. Any
You
questions?
have the ordinals also, the cardinals versus the ordinals.
Which are better.
No.
Most important set theoretic question.
Yeah.
How do I unshare screen? Though I guess I shouldn't unshare screen yet, just in case I need to refer to any of the slides.
I mean, this is maybe a bit of a like, I don't know, big picture, vague question, but you motivated this a lot, it seemed, by philosophical concerns. And so do you ultimately think that this sheds some light on, trying to identify the standard model of arithmetic, or do the various caveats you mentioned along the way undermine that?
I guess your mileage will depend on what you already believed coming into this. For me, like I'm already a pretty strong Platonist as it is, so I'm finding an implication between two things I already believe, that there's a true notion of arithmetic and a true notion of randomness. But okay, well, one thing that I'm not super Platonistic about is the entire background theory of sets. So again, it'd be take way too long to really go into this idea, but one of the things I've really been trying to focus on in my research is this idea of directly formalizing this concept of Platonism about coin flipping without directly talking so much about the background universe sets. So that is something that I think a lot about, and I do take Platonism about the coin flips themselves very literally, and I do like that it implies that it gives us a way to cut out the true naturals. And there's a similar thing for the continuum, where if you give me two different models of set theory with the same naturals, let's say it's the truest naturals, but one has a bigger continuum than the other, then the smaller continuum is actually going to be perfectly small inside the larger one, and also absolutely negligible. So this gives a quote unquote test for having the true power set, where you just hand me a model of set theory in the ether, and I coin flip on a set X, and with probability 1, I get a subset that's in the model you handed me, if and only if it was correct about the power set in the first place. It doesn't let me build the true power set. It only lets me test if it's the true power set.
Awesome, thank you.
Anyone else? Okay. Let's thank our speaker again. So thank you very much again. Next week we have a joint talk from Alessandro Berarducci and Marcello Mamino on a new proof of incompleteness. I guess using model theoretic methods. Looks interesting. So same time. So please be here for that. So and again, the recording for this will be up on YouTube shortly, probably tonight or tomorrow.